Hello Gators, we're going to be learning about rates of change in applied context other than motion, other than velocity and acceleration, and we're going to have an introduction to related rates. Let's take a look at something we've seen before. To know if something is increasing or decreasing, check the sign of the derivative. And in context, you're going to be looking at its derivative. Now, if you're looking at height increasing, you're going to be looking at the height, the derivative of height, and if you're looking for increasing, you're looking at when it's greater than 0. If in the problem you're looking at velocity decreasing, you're going to be looking at velocity with respect to time less than 0. See, these are the things that we look for in increasing and decreasing. Let's take a look at this problem. The store is having a 12-hour sale. The total number of shoppers who have entered the store T hours after the sale begins is modeled by this function. A, at what rate are shoppers entering the store 5 hours after the start of the sale? As soon as you see the word rate and you see at 5 hours, consider a derivative. So we will take the derivative of E of t using our power rules, and then we'll substitute 5 in there. So the rate will be 200 shoppers per hour entering. Since it's positive, then we're getting an increase of shoppers coming in. B, explain the meaning of E double prime of 5. Now, E double prime is a second derivative. We'll be taking the derivative of the first, but more important, we want to know the meaning. The second derivative will be, again, to use the power rule, and if you put 5 in, it'll be 715 shoppers per hour per hour. And what does this mean? Well, it represents the rate at which the rate of shoppers entering is increasing at 715 shoppers per hour per hour. Let's take a look at rate of change from a table. If we're looking to estimate the rate of change at 15, we can see 15 is not in the table, so we'll use the numbers that are next to it. So we'll do P prime of 15 is approximately, and we'll do the rate of change of P of 20 minus P of 10. So that's the change in y over the change in x, which is 20 minus 10. So this value will be 150 minus 120 all over 10. And then this answer is 30 over 10, or 3 people per year. Okay, so now to estimate P prime of 20, notice that 20 is given in our table. And we have some options. We can use the numbers around 20, or we can actually use 20 itself. Let's take a look. You can see that if I use the numbers around 20, I will do P of 30 minus P of 10, all divided by 20, and that'll be 4 people per year. You can also just use the number 20 and use a number right that it's next to. So we could use 10. In that case, you would get 3 people per year. P prime of 20, if you use the other side, 30 and 20, you would get 5 people per year. Remember, this is just an estimate. So all of these are really good estimates of the instantaneous rate of change at 20. Many variables have a familiar relationship, like the Pythagorean theorem. These variables are related to each other. A squared plus b squared is equal to c squared. The variables are related. Today we're going to talk about rates being related to each other. So in a triangle, remember the sides, a squared plus b squared equals c squared. The sides are related to each other. Let's talk about the rates being, and sometimes when we take a rate of change, we take it with respect to time. A lot of times that's done with time. So we're going to take the derivative with respect to time of this side and the derivative with respect to time on this side. Now, this is called implicit differentiation because you're treating A, B, and C as differentiable functions. So this will be 2a, and then take the derivative of the inside function, dA dt plus, we're going to take the derivative of b squared, treat b as a differentiable function, 2b dB dt, and then we'll take the derivative of c squared, treating c as a differentiable function, 2c dC dt. Now this is what we call a related rate. We have three rates that are related to each other in this equation. Just like in the Pythagorean theorem, the variables were related to each other. Let's take a look at a problem where a police car is approaching an intersection. So the police car is approaching this direction and a car is speeding up in this direction. And we would like to set up a relationship that finds an equation that shows the related rates of the vehicles with respect to time. So let's call this a y change, and let's call this an x change. And the change in their distances from each other we'll call a z change, very similar to A, B, and C. So the first step is to write out the relationship of the variables. So x squared plus y squared is equal to z squared. This is the relationship with the variables. Now I'd like to take it to the next step, the calculus step, which is to take a look at their rates. How do their rates relate to each other? Which means I am going to take the derivative with respect to time. And this is going to give me an idea of motion. And in this case, we're going to do something very similar to what we did a few minutes ago. I'm going to treat x as a differentiable function. Now remember, it's with respect to t, so x is going to be 2x, and then you have to take the derivative of the inside variable, which is dx dt. And then we're going to do it with y, 2y dy dt. And then we're going to have 2z dz dt. And now what we have is a related rate. We have all of these rates, this one, and this one, and they're related in this equation. And in our next lesson, we'll find values for those that'll help us solve what we want to know. Let's take a look at this ladder problem. The ladder is leaning against the wall and starts sliding down. Relate the rate of change in the vertical and horizontal distances, and this is with respect to time, that the ladder makes with the wall. So we're going to call this y again, and we're going to call this x change. And so the relationship between all of these is x squared plus y squared, but instead of saying z, I'm going to say 10 squared. And the reason why is because this hypotenuse is not changing. It stays the same number. All right, now I'm going to rewrite the problem because my next step is to take the derivative with respect to time. So I'm going to take the derivative with respect to time of this side and take the derivative with respect to time of this side. All right, this answer is going to be treat x as a differentiable function, 2x dx dt plus 2y dy dt, and this derivative of a constant will be 0. So now we have an equation that relates these two variables, dx dt and dy dt, in this relation, and this is called a related rate. Let's take a look at these problems. So when we approach these problems, we want to set up a relationship with the variables, and then we want to differentiate with respect to time. In this problem, we're talking about an ice cube, and an ice cube is a three-dimensional figure, and we're talking about volume, which tells us that it's three-dimensional, and we would like to look at the rate of change with its edges. So we want to relate the change in volume with the change in edges. So our first step is to set up a variable relationship, and a variable relationship for a cube, the volume of a cube, is v equals s cubed. So I'm going to rewrite it here. And then my next step is to take the derivative with respect to time. So this would be the derivative with respect to time on this side, derivative with respect to time, and this is called implicit differentiation. So then this will be dv dt, and remember we have to do the outer function. This is going to be a chain rule, so this is 3s squared, and then you got to take the derivative of the inside function, which is ds dt. At this point, we have an equation that is relating the two rates of dv dt and ds dt. All right, let's take a look at the next one. The width and length of a rectangle are increasing. We want to relate these rates of change with the rate change of the area of the triangle. So I'm going to write it out again, and then I'm going to find the derivative with respect to time of each side. The derivative with respect to time on this side, derivative with respect to time on this side. All right, and then again, treat a as a differentiable function, dA dt. And then for this one, I have to remember I'm using a product rule. I have two functions, an L and a W. I'm going to leave the L alone, and I'm going to take the derivative of W, dW dt, and then I'm going to take the derivative of L, dL dt, and then times it by W. And now I have an equation that relates three rates of change. The rate of change for area with respect to time, and length with respect to time. And this is the end of the video.